Hi everyone. In this video, we're going to talk about Lab 2. In Lab 2, we're going to investigate a voltage divider, a current divider, and then we're going to simulate it using MATLAB. Then compare those results, your theoretical results that you find in pre-lab, and then your experimental results that you find using this procedure that we're going to do here, and then compare it to the simulations, and then report that. Okay. So let's get to the voltage divider. Here we have a circuit and we want to create a 12 volts, 7 volts, 2 volts, and if you've done the pre-lab, you should have derived some resistors for here. Make sure to check your resistors with the right answer so that for the actual procedure of the lab, you use the correct resistances. So if we do the calculations, we need an R1 of 90 ohms, R2 of 150, R3 of 150, and then R4 of 60 ohms to create those voltages of these levels. Okay. Okay, so now let's get started and create this circuit. So first of all, we need a voltage source of 15 volt, and we're going to create this the same way that we did in lab 1. So I already have the setup here, and the setup, nothing changed in the setup since lab 1, so it's the exact same setup. And I'll give 5 volts here, and I'll go into the input of the DC-DC converter, and it'll give me a 15 volts, which will run through these two vertical sockets, basically type 2 sockets. So to create the 5 volts, again, similar to lab 1, we're going to use the batteries and the battery holder. Okay. Okay, so let's plug this in here. So let's go to the negative and positive. And now I know that my setup is correctly wired, and then I put the batteries in. Okay, so this is off. And so when I turn this on, these two rails should become 5 volts. And these two rails should become 15 volts. And I'll verify that by measuring them. So if you remember, we take this to 20 volts, and then we're measuring DC current and DC voltage. Okay, so I'm going to plug this in here. Okay, so I'll turn this on. Yeah, so I'll get I have the 5 volts here, and I should have the 15 volts created by my DC-DC converter on these two rails as well. 16 volts with some error tolerances, and which is fine. Okay. So I turned the circuit off. I turned the battery holder off because I want to perform tasks on my circuit right now. I want to basically connect these resistors, and then I want to work on my board. So I turn this off, so there's no energy flowing through my circuit. Okay, so let's put this away. All right, so now we need to create our R1, R2, R3, and R4 that I showed from the pre-lab from this list of resistors, and you're given all of these resistors in your lab kit, so you have access to all of those. And you can find the values of those resistors by using the color codes, which you can find at the end of this document, or you can just use this multimeter to measure its resistance. Okay, so let's go back and okay, R1, R2, R3, R4. Let's see what we need for them. So for R1, I need a 90 ohms, and I can create them based on that table. I can create it with 101 kilo ohm resistor, which I have already prepared. And then for R3, I'll need R3 and R2, I'll need 150 ohms. And I can make this in two ways. One is I can have two 100 ohms in parallel and then make that in series with another 100 ohms, which will give me 150 ohms, just here. And then for R3, I'll need the same thing, 150 ohms. But we only have three 100 ohm resistors. So I'll just create that with the 220 ohm and then 470 ohm resistor, which will give me very close, which will bring me very close to 150 ohms. And then for the 16 ohms, I can use just 220 ohm resistors, which is this. Okay, so this is R1, R2, R3, R4. And then let's go back and create our circuit. So first I have R1, so I'll start from here. So I'm gonna use row 20 and row 25. And so the 100 ohms and the 1K are in parallel, so I'm going to use basically the same thing, connect the two ends of both of them to rows 20 and 25. And that's R1. Now I want to connect R1 in series with R2, R3, and R4, so I'll just do the same thing over and over. So for R3, I'll do this with, I'll connect it the 100 ohms to 25 rows 25 and 30. Then I'll do the same thing for the 100 ohms in parallel, because we have 200 ohms in parallel and then one in series, right? Okay, so I have these 200 ohms in parallel. So basically, I'm just creating this right now, and then I have to make it in series with another 100 ohms. Okay, so I connect this one to row 30, and then this, and to row 35. Next, I'll have another 150 ohms, and this time I'm going to use the 220 ohm and then 470 ohm, which both of them are in parallel. So one end to 35, then the other end to row 40. I'll do the same thing for the other resistor. So these two are now in parallel. Okay, and R4 is 60 ohms, so which I'm using 220 ohms in parallel. So row 40 and row 45, and row 40 and row 45. Let me bring this here. Not matter, but they're next to each other. Okay, so these two are in parallel, they create the 60 ohms. These two are in parallel, they create 150 ohms. These three create the 150 ohms. Then these two create the 90 ohms. Now I have to connect the positive rail of the 50 to R1, and then the negative rail to R4, right? So I'll get two wires. I'll get a red wire and a black wire. So I'll connect the black wire, the ground, to, this is R4, and then I'll connect it to the negative terminal, right? And then basically I'm going to connect the row 20, which is the positive rail, to which is the rail for R1, and then connect it to the positive rail of the 15 ohms. Okay. So now I have my setup ready. Okay, so now plug this back in. And so what we want to do now is to make the measurements of the 12 volts and the 7 volts and then 12 volts and see if they are different from what we expect to be. And if they are, you should explain why those differences are. I'm first going to set the multimeter so that it measures the DC voltage. And I'm going to measure the voltage across R4, and you guys can repeat the measurements for the 7 volts and then 12 volts and give your answers. So let's turn this on and see the voltage across R4. So we'll see that the voltage is about 1.9 volts. And so there are some deviations, and in your report you should explain why these different deviations are. So one thing to like, for example, you had 15 volts here, but we measured the input voltage here because of the tolerances of the DC-DC converter. You have some tolerances. You had the 16 volts. That's one factor. There are other factors like the resistor tolerances that you have to look at it and see how much that tolerance is based on the colors, and then yeah, do the same thing for the 7 volts and the 12 volts. Okay, so this is it. So let's turn this off, and then we'll go to the current divider. Okay, so now we construct the current divider and measure the currents in each branch. So in order to create these currents from your pre-lab, the 16 and the 10 and then 6 milliamps, you need the resistance values of these, which are given in the pre-lab solution: R1 700, R2 1167, and then R3 1750. And so the closest value we have to the 700 ohms is the 1680, which is close enough, and 680 ohms, which is here. And then the closest we have to the 1167 is the 1200 ohms here. And then how we can construct the 1750 ohms with these three resistors in series here, which are the 1200, 330, and the 220 ohm. Okay. So we have a 100 ohm resistor in series with our 15 volts, which I have it here. Okay, so now let's construct this circuit. So take the 100 ohms and then put it between 15 and 20. And okay, so I'll take the R1, which was the 680 ohms, then connect it to row 20 and row 30, and I'll connect R2, which was the 1200 ohms, to again in parallel with R1, right? So to rows 20 and 30 again. And then I'll need to connect these three resistors in series to construct the R3, right? So I'll do that in the right side of this type 1 socket strip, because so I'll connect this to row 20. So the right side, which here is not connected to the left side, right? So these are separate. So connect these three in series here. So row 20 and 25. And 25 and 30. And 30 and 35 here. So now I want to connect these two ends because this three in series construct R3 for me, and these three will be in parallel with this. So I want to connect these two ends to these two ends. Take two jumper wires and connect these two together, like so. Okay. So now I have my circuit. Wait. So we have to connect the 15 ohms, the 15 volts, the positive 15 volts to the 100 ohms, which I'll do with the red wire here. So this is going to be 15 volts to the 100 volts, and the negative terminal of the 15 volts to here, which is our ground. I can connect it here, or I can connect it here. I'm going to connect it here because there's more pins here. So these two nodes are connected through these wires, so it doesn't matter. So this is ground and this is ground, and now with this black wire, the negative terminal is ground too. Okay, so I constructed this right now. And okay, so let's put this in. And so if I turn this on, the circuit will start, but we want to make the current measurements in I1, I2, and I3. And to do that, we have to connect the ammeter in series with R1, R2, and R3 and make the measurements. So because all the amperes here are less than 20 milliohms, so I'm just going to put this on the 20 milli and then ampere, DC ampere. And first I'm going to attempt and measure R1. In order to measure R1, this ammeter has to be in series with R1. So this was my R1, and then I connected it between row 20 and row 30. So I'm going to break this connection to the ground and then bring this, basically I took the pin that was connected to row 30 out and I'm connecting it to row 25. Okay, like this. All right, and now I'm going to make this ammeter in series with this R1. So I'm going to connect this to row 25, the positive end of the ammeter, and I'm going to connect the negative end of the ammeter to row 30, which is my ground. So I'm basically cutting this wire here, and then connecting my ammeter in between the R1 and then the ground, right? So the positive terminal is connected to of the ammeter is connected to R1, and the negative terminal is connected to ground. Okay, and yeah, so that's basically it. And then everything is set up. We can just turn this on, and for R1 we expect about 16 milliamperes, something about that, which is about what we get with some deviations, and again you have to talk about the deviations. So repeat the same thing for R2 and R3 and find the currents in uh, I2 and I3, the measured currents, and um, compare it to your calculator, what you expect them, and then explain why they are different or similar, or however you find the results. So just make sure whenever you want to change the setup and to make the measurements in another branch, turn this off, and then always work in a non-energized circuit. So for example, if I want to make the measurements in R2 or I2, so I take this ammeter off, I connect back my R1 to ground. So I have this again. So basically I took this out and then connected to row 30 again. And so I'll do the same thing for R2 here. So I'll take this one end out and then connect it to row 25 and then connect this in between here and then make the measurements. And I'll do the same with R3 and make this ammeter in series with R3 to make the measurements. Yeah, that's it for the experimental part of measuring the voltages and currents for the voltage divider and current divider. So yeah, make sure to turn this off. Turn this off when you're done. When you make all the measurements, and always, as always, make sure to take the batteries out of the battery holder. This is an important step, safety step. So make sure to take this out. And yeah, so next we're going to talk about the simulation part, and we're just going to simulate the same circuits in MATLAB, and yeah, see how that goes. So now we're going to simulate the current divider and the voltage divider circuit in MATLAB. And the University of Calgary has an active MATLAB license for all the students. You can go to this link here and download MATLAB and install it on your personal computers. Then you'll be from University of Calgary, you'll have a license. But you have to also create a MathWorks account, which you can do from this link here. Once you do that and you install MATLAB and open it, this is what should come up. And make sure to go to apps first, this app, and then get more apps. The add-on explorer will open, and from here just click clear filters. So there's no filter, and search for Simscape electrical. Okay, so you have to install this one as well. So I've already installed it, as you can see. Make sure to go in here and install this. And once you do that, go back to the MATLAB homepage. And from here, we'll start the Simulink, start Simulink here. Okay. And so we're going to create a blank model. And first thing, we're going to name the model, save the model. So go to save, and so MATLAB, ENGG225-lab2, I've already made some. So maybe name it as, so let's first create the lab2 voltage divider. I'm going to name it lab2 voltage divider. And so first we're going to create the voltage divider. Okay, save. Now we have to bring in the elements in the voltage divider, which were the voltage source, the resistors, and other elements, right? So we can do that by going to the library browser here. And so minimize this. So first we'll go to Simscape here, then expand it, and then we'll go to electrical, expand it. And first we're going to find the voltage source from the sources here. So we'll have the current source here, but we're looking for the voltage source here.
So there are two ways to add this to your model. One is just drag and drop like this, or another one is to right click and then choose add block to model lab2 voltage divider to your model, right? So I'm going to use this one. So I added the voltage source. Now I need resistors, right? So I'll go to the SimScape passive, and in here I find resistors. I'll add that. I'll also need some sensors, a current sensor and a voltage sensor, and I'll need an electrical reference. So from electrical connection and references you can choose add block to model lab to electric. So all of these were under the SimScape electrical. Now close this electrical, and then under SimScape and utilities add PS to Simulink converter. I'm going to explain later on what this is, and add the solver configuration to your model. Now close this SimScape and then go to Simulink, open it up and go to sync and add a scope. Right. So as you can see, all the elements came on top of each other, so you can just separate them by dragging them. Okay, so now we have to create, we want to create the voltage divider circuit, which we had. So we want to create this circuit here, and then measure the voltage across R4 and then here. So if you remember, this was 2 volts, and this was 7, this was 12, and so we had the 15 volts. So we want to create this this circuit here. Okay, so let's get started. So I have a resistor here, and so Control C, Control V, and then you just copy and paste another one because we have 4 resistors, right? And then Control R will rotate it. We will have Control C, Control V again to paste 2 more resistors. And so electrical reference comes here, and okay, and I want to measure the current. This is not asked, but I just want to measure it to have the current that's flowing through the circuit. Okay, now let's connect these up, and this is our circuit, right? So this is what we have in the circuit. So make sure to always, the solver configuration has to be connected to one of the nodes. Typically they connected to the ground node. If you don't have this connected, you won't be able to run the simulation, so make sure to have this connected. Now we want to connect the voltage source across this. You can use Control I or Control R to rotate or flip this the way you want. So I'm going to use this. Now this is the voltage source, and I want to view this in a scope, the waveforms of this voltage source. However, this voltage source was from the SimScape library that we had here, and the scope is from the Simulink. So we have to use a converter to convert the signal in the SimScape to Simulink, and that's where this one and this PS to Simulink converter came into play. So now we connect the voltage source to this, and then from here to our scope. And we'll repeat the same thing, Control C, Control V, for the other measurements that we want to do. Right. Okay. Okay, we're gonna need and The same thing for the current probe too. Right, okay, now we have to give the values of the DC source and the resistances, right? So in the resistor we had 15 volts here. So resistor was 15 volts, and this resistor was R1, we found it to be 90 ohms, and R2 we found to be in pre-lab 150 ohms, R3 150 ohms, and R4 was found to be 60 ohms. Okay, so if we put these resistors and a voltage, DC voltage of 15 volts, remember the DC voltage, the AC voltage peak amplitude has to be 0. Okay, so we expect a voltage of 2 volts here, 7 volts here, and 12 volts here. So let's run this and see how it goes. Okay, so this is finished. Double click on the scope, and then you'll see that we'll have a DC voltage of 2 volts here, and this is exactly what we expect. To make better measurements, you can go to here and see the signal statistics from here. So the mean value is 2 volts, the maximum and minimum are the same because it's a DC voltage. So we have the 2 volts. So as you can see, this is actually a good method to check your work for your assignments as well. So you can just build the circuit, and then you do your calculations, and then after you do your calculations and you find, for example, a voltage across a resistor, you can just verify it by doing the simulation. You have to get this same exact answer because these resistances and the voltages and everything are ideal. So you get the same thing. So if you double click on the other one, so you have 7 volts here. Again, if you go to the signal statistics, you'll get 7 volts, which is what we exactly expect to be. And same for here, 12 volts it should be. We could also use the cursor from this here, and so you'll have 2 cursors. Cursor number 2, you'll see this value here changing as I change this. This is the time, and this is the voltage here, 12 volts. You'll have cursor 1 here, which the time here changes, and then its value here also changes. So you can make the measurements using this or at signal statistics from here, which gives you the 12 volts. Okay, so this is it for the voltage divider. Next we're gonna go to and explain the current divider. Current divider, let's create a new model. So let's save this first. Then we go to new, just a new model. Now let's save this model the same way that we did for the first one. ENGG225-lab, and then here we can say lab2 current divider, and because I have one of these, I'll just name it 001. And so lab2 current divider, and then save it. Next, again, we want to add the elements and the components. So we're going to go to the library browser here, and then first we're going to go to Simscape, open it up, and then go to electrical, and first we're going to need a voltage source. And here it is. Okay, and then we're gonna need resistors. Just gonna add one because then I can just use copy and paste, Control-C, Control-V to add more. And we're gonna need current sensors, add this in there, and electrical reference from the connectors and references. What else do we need? I think that's it from here. We close the electrical, go to Simscape Utilities, we add the PS to Simulink converter and the solver configuration. You always need the solver configuration. And let's close this, go to Simulink. Under Simulink, go to Syncs, and from Syncs you can find Scope. Add this. Alright, so we have the components that we need, and we just can make copy and paste. So now let's create our circuit, the voltage divider circuit. So if you remember the voltage, the current divider, sorry. So we want to make this circuit here. So 15 volts, 100 ohms, and then R1, R2, and R3. Okay, let's go back here. All right. So Control R to rotate, and then Control C, Control V to paste, and then I want to measure the current in each branch of these resistors, right? So I have to have this this ammeter in series with each resistor. So I have this, and then same as before, this goes to a PS to Simulink converter, and then from that this goes to a scope. So I need 3 of these in parallel. Control C, Control V, Control V. Okay. Right, now let's connect everything up. Oops. Alright, so the solver configuration, we usually connect it to the ground, and then connect the other ends of the ammeter. Now let's put in the values for the voltage source and the resistors. We can go here, and we have a voltage source of 15 volts. Then this resistor right here was 100 ohms. And then R1, R2, and R3. R1 we calculated to be 700 ohms. So we'll put 700 here. And yeah, so we used 680 ohms in the experimental part, and we found the in the pre-lab that it should be 700. Let's just put what we found in the pre-lab here. And R1, R2 we found to be 1167 ohms, and then R3 was 1750. Okay, so everything seems to be okay. Now let's run this and see the currents here. Right, so let's open this up and let's go to the signal statistics. Because it's a DC current, its DC is equal to its mean, and you can see that the current is 16.67 milliamperes, which is exactly what we expected from our pre-lab, right? So again, you can just double check your work using simulation. If you're doing the assignments or anything else, you can use the simulation. It's very good. And you can just play with it and give different resistances, different voltages to see how this current changes and everything else. And you can repeat this for the other scopes to show the so you can see here you have 10 milliamperes, and which is what we expected, and here can't see it from the graph. Let's go to signal statistics. Here we have 6.67 milliamperes, which is again what we expected. Yeah, thank you very much.